A magnetar can pull a planet's memory away from halfway across the solar system. These things have magnetic fields a quadrillion times stronger than Earth's. Forces that immense, they warp the fabric of atoms themselves. These stellar corpses act as the universe's ultimate physics lab. They test the laws of nature under conditions we can't recreate. When a star dies, it can leave behind a magnet powerful enough to twist light, powerful enough to materialize particles from empty space, and the question becomes how our understanding of reality holds up. Faced with that kind of absolute cosmic power, that final collapse creates something truly alien, a city-sized sphere of pure neutronium, a material so dense, a sugar cube of it would weigh more than all of humanity. That's a neutron star, the compressed heart of a giant, but within that family there's an even more extreme class, a magnetar. The difference comes from the first few seconds after the core gives way. In that catastrophic birth, the newborn star's interior is a superfluid, superconducting soup. It churns like a dynamo, and if conditions are right, that turmoil can amplify the star's original magnetic field, twisting it, winding it, until it reaches a staggering intensity. We're talking about magnetic fields measuring a quadrillion Gauss. For perspective, the magnet on your fridge is about 100 Gauss. An MRI machine, which can lift a chair across a room, operates at 10,000 Gauss. A magnetar's field is a 1 followed by 15 zeros more powerful. Astrophysicist Victoria Caspi described it. Magnetars are in a league of their own. They are the magnets of the universe. Everything else is just fridge decoration. And this unimaginable force is trapped inside an object spinning at a blinding pace, sometimes completing a full rotation in mere seconds. Its surface is a crust of iron, a billion times stronger than steel, cracking under the strain. From this tortured environment leaks a steady drizzle of X-rays, and occasionally, without warning, the rigid crust will snap, a starquake. That releases a giant flare. A burst of energy that can outshine our entire galaxy for a fraction of a second. These are the fingerprints astronomers use to identify these monsters. Their very existence forces a question. What happens to the fabric of matter when it's subjected to a magnetic force so strong it becomes the dominant feature of reality? The first clue came from a watchtower, not a telescope. It was during the Cold War. A fleet of American satellites, the Vela satellites, were orbiting Earth. Their job was to watch for the flash of a nuclear test. They were built to monitor our own destructive power, but they started seeing something else. Something far more powerful. In the late 70s, analysts saw these spikes, intense spikes of gamma radiation. They were coming from deep space, not from Earth. And they didn't match any weapon. They were cosmic, and they were a mystery. Then, on March 5, 1979, the instruments went wild, a surge of radiation. So intense it saturated detectors. Across the inner solar system, it came from the direction of the Large Magellanic Cloud. That's a small galaxy orbiting our own. The initial pulse was over in 1/10 of a second. But then, the afterglow, it oscillated with a precise rhythm, an 8-second rhythm for minutes afterward. That rhythm was the key. It was the spin of a star. This event, the March 5th burst, was a revelation. It was hundreds of times brighter than any known cosmic explosion. For a moment, it outshone every star. In every galaxy we could see, and then it faded, but the story wasn't over. Other bursts were detected, similar ones. And they weren't single events, they repeated. These objects got a name, soft gamma repeaters. The repetition was the critical detail. A one-time explosion, like a supernova, that's a final act. But something that erupts again and again, that's a system. It's an engine with a fuel source, a structure under immense stress that periodically cracks. Astronomers realized they were looking at the tantrums of a single object, an incredibly dense object, a magnetically tortured object, a neutron star with a difference. The discovery of these repeaters rewrote the chapter on stellar corpses. It proved some neutron stars weren't just inert cinders. they could harbor these unimaginable magnetic reservoirs. Acting as cosmic pressure cookers, the energy for those flares, the galaxy-shaking flares, had to come from somewhere. That somewhere was a magnetic field of almost impossible strength, bending the rules of physics itself and waiting to be understood. That 8-second rhythm, it was a death knell, a stellar heartbeat. And it told astronomers the source was small, dense, spinning, a neutron star, but the power of the burst, the fact it repeated, pointed to something more extreme. To understand that, you have to go back to the violent forge where these things are born. The story starts with a spectacular failure. A star, 8 to 30 times the mass of our Sun, burns for millions of years. It's a cosmic pressure cooker, fusing lighter elements into heavier ones, hydrogen into helium, helium into carbon, all the way up to iron in the core. Iron is a dead end. Fusing iron doesn't release energy, it consumes it. So when the core becomes solid iron, the star's engine dies. Gravity, held back for eons by nuclear fusion, wins in an instant. The core collapses. In less than a second, an object the size of Earth is crushed down to the size of a city. Electrons slam into protons, creating a dense sea of neutrons. The outer layers of the star, now unsupported, come crashing down at a quarter the speed of light. They hit the new, impossibly hard neutron core and rebound. A shockwave. This is a supernova. An explosion that can outshine a galaxy. In that chaos, something special can happen. If the original star was spinning fast and had a strong magnetic field, its final moments act like an amplifier. As the core collapses, the conservation of angular momentum takes over. Like a spinning ice skater pulling their arms in, the star's original spin is magnified tremendously. The newborn neutron star can be rotating dozens of times per second, and at the same time the magnetic field gets squeezed, wound up. The star's interior in those first seconds isn't a solid ball. It's a superfluid, a frictionless quantum soup of neutrons swirling with tremendous energy. This churning, combined with the frantic spin, acts like a dynamo. Imagine the most powerful generator you can conceive, built on a planetary scale, spun at relativistic speeds. That dynamo effect twists the magnetic field lines, pumps them with energy, amplifies them to strengths that defy belief. This is the stellar lottery that creates a magnetar. It's not the fate of every massive star. It requires the right combination: mass, a rapid initial spin, a strong magnetic heritage. When all those factors align in the supernova crucible, the result isn't an ordinary neutron star. It's not a pulsar, it's a magnetar, a cosmic accident of such immense power that its very birth sets the stage. Its magnetic field isn't just a property. It is the defining feature, an engine of destruction woven into its structure from the first second. The scale of that number is almost meaningless to us. A quadrillion times stronger than Earth's field. You need a consequence to make it tangible. A simple refrigerator magnet, that's about 100 Gauss. It can hold a piece of paper to a door. A hospital MRI machine, a massive device that operates at around 10,000 Gauss. That's the peak of our magnetic technology here on Earth. A magnetar's field is a 1 followed by 15 zeros more powerful. 10 to the 15th power Gauss. It's in a realm beyond our technology, beyond most of our physics. If you could bring a magnetar to a point halfway between the Earth and the Moon, its influence would be catastrophic. Not through gravity, but through magnetism. From that distance, its field would still be strong enough to scramble the magnetic strip on every credit card, every hotel key, every hard drive on the planet. A global, silent erasure of magnetic data. But that's just a parlor trick, a side effect. The real power is what it does up close. At these intensities, a magnetic field stops being a simple force that pushes and pulls. It becomes the primary environment. The energy stored in that twisted field is so immense its density warps the structure of spacetime around the star. It creates a pressure that rivals the gravitational pressure crushing the star's core. So the field itself begins to dictate how matter can behave. It starts to affect the quantum vacuum, that seething foundation of all space, constantly spawning fleeting pairs of particles and anti-particles. In a field this strong, those virtual particles are no longer just mathematical ghosts. The magnetic force becomes so powerful it literally rips them into existence, materializing matter from empty space. That staggering strength isn't just a record-breaking statistic. It's the master key that unlocks doors to realms of physics we can only theorize about. It warps the very definition of something as fundamental as an atom. The atom we know, that stable sphere of electrons, it's an illusion. It only works in our gentle universe. It can't survive near a magnetar. Here, the magnetic field isn't a guide, it's the architect, the supreme architect of reality. Its force is so overwhelming it redefines the shape of matter itself. To see how, picture the forces in a simple atom. You have the negatively charged electrons in orbit, held by their attraction to the positive nucleus. That's the Coulomb force. It's a stable system, it's balanced. But then you introduce a magnetic field of magnetar strength. That balance is shattered. The magnetic force on the electrons becomes trillions of times stronger than the force binding them to the nucleus. It's the difference between a breeze and a hurricane. The hurricane wins. What happens next is a distortion of the atom's architecture. The electron orbitals, those cloud-like regions where an electron is likely to be, they're violently reshaped. In our world, these orbitals can be spheres or dumbbells. Near the magnetar, they're stretched. They're pulled into long, thin needles, all of them aligned perfectly with the magnetic field lines. The whole atom is no longer a sphere. It becomes a cigar, a long, skinny thread of matter, forced into that shape by the will of the magnetic environment. Physicists call this magnetic confinement. The atom is imprisoned within the geometry of the field. This isn't a subtle change. It's a complete rewriting of the rules. Chemical properties are dictated by the shape and behavior of the outermost electrons. They decide how atoms bond, what molecules they form, whether something is a metal or a gas. But when every atom is stretched into an identical, needle-thin filament, that rulebook is burned. Hydrogen can't bond with oxygen to make water. Carbon can't form the chains of life. The very concept of chemistry as we understand it ceases to have meaning. The matter here enters a new state, magnetized matter. It's a form of material that can't exist naturally anywhere else in the cosmos. A direct creation of the magnetar's absolute dominion. That's the field's true power. It doesn't just move matter, it redesigns it from the subatomic level up. It crafts a universe where the laws of our reality are just suggestions. The reshaping of matter isn't quiet. It makes a sound, a cosmic scream. The crust of a neutron star, it's not like anything here. It's a lattice of iron nuclei, a material a billion times stronger than steel. But even that shell isn't immune. The magnetic field is anchored deep in the core. A superfluid core, but it threads up through the solid crust, like 1,000 steel cables frozen into ice, and they're being twisted from below. The crust is locked onto those lines of force. So as the star spins, as the field writhes inside, the stress builds. It's a pressure cooker with walls of iron, straining until something gives, and it does give. Suddenly, the crust cracks. A fracture races across the surface. A city-sized star, probably spanning the whole circumference. That's a starquake, a seismic event. On a scale that dwarfs any earthquake we could have. In a fraction of a second, the crust shifts. It settles into a new state, slightly lower energy. But the energy released, it's almost beyond comprehension, equivalent to the sun's total output. Not for a year, for hundreds of thousands of years, all unleashed in a flash. That energy doesn't come out as sound or shaking. It erupts as radiation, the highest energy radiation. X-rays and gamma rays, that's the signature astronomers detected. From across the galaxy, those soft gamma repeater bursts, those anomalous X-ray pulsar flares, they aren't random, they're the direct consequence of a starquake. Each flash is a seismic event, on a stellar corpse, a telegram, announcing a structural failure, but for scientists, these events are a gift. It's cosmic seismology. Like geologists studying seismic waves to learn about Earth's interior, astrophysicists can study the X-ray pattern after a starquake, the way the light flickers and fades. It tells a story. It reveals the crust's thickness, its elasticity, the nature of the exotic particle soup swirling beneath. Each starquake is like a hammer tap on the side of a giant, dense bell. The ring tells us what the bell is made of. So these magnetars, in their violent growing pains, they are doing more than demonstrating power. They are probing the limits of matter, conducting experiments in physics at nuclear density and broadcasting the results across the universe. In flashes of light we're just learning to decode. Every crack in that iron crust is a message, a violent, luminous clue about the true nature of the cosmos. Light bends to a magnetar's will. Space itself changes character around it. The vacuum isn't truly empty. Quantum electrodynamics says it's a seething foam. Virtual particle pairs wink in and out of existence. In our world, they're fleeting. But near a magnetar, the magnetic field is so strong it seizes that activity. It polarizes the vacuum, forces it to behave in a strange new way. The vacuum becomes like a crystal. That's vacuum birefringence. Imagine shining white light through calcite. The crystal splits it into two beams, different polarizations. The magnetar's polarized vacuum does the same. Light splits into two components. They travel at slightly different speeds. The fabric of nothingness has an index of refraction. It bends light. So a photon from the surface doesn't travel a straight line. Its journey is through a distorted medium, a hall of mirrors built from pure force, and it gets stranger. In these extreme fields, photons can interact with virtual particle pairs in ways that are impossible elsewhere. They can merge, split, even become momentarily trapped, their energy borrowed to create real matter from the void before annihilating back into light. The light we might see from a magnetar's environment isn't a pure signal. It's a transformed messenger, carrying the scars of its passage through a rewritten reality. For astronomers, that distortion is a gift. The altered light, its specific polarization and energy signature, is a direct fingerprint of the magnetic field that shaped it. We can't visit a magnetar, can't recreate its power in a lab, but by analyzing the light that escapes its grasp, we can decode the conditions that created it. Each photon becomes a data point from the edge of known physics. The magnetar, in its terrible isolation, is running the experiments for us, testing the predictions of quantum electrodynamics under conditions we'll never achieve. Turning the cosmos into the ultimate laboratory for understanding the union of light, matter, and force. A spacecraft getting too close, it wouldn't just fail. The magnetic field starts working long before you even see the star. As you approach, that field begins to polarize every atom in the hull. Each atom gets stretched into a thin needle. They all line up perfectly with the magnetic lines, and this isn't gentle. It's a violent command at the molecular level. The bonds holding the metal together, the lattice that gives it strength, they face stresses they were never meant to handle. The hull wouldn't just buckle. It would be torn apart from the inside at the level of individual molecules, any complex material. The plastics in the consoles, the organic matter of a cruet would face instant dissociation. The blueprint of DNA, those long polymer chains, they'd be unraveled in a flash, their chemical identity just erased by the overwhelming magnetic will. Then for conductive material, a second process takes hold. A changing magnetic field induces electrical currents, and near a spinning magnetar, the field isn't just strong. It's violently dynamic, whipping past at relativistic speeds that would induce colossal currents in the ship's frame, currents so immense they'd turn the hull into a superheated plasma. Instantly, the vessel wouldn't melt. It would vaporize, so the end result isn't a ship. It isn't even debris, it's a diffuse cloud, a plasma of bare atomic nuclei and disassociated electrons. Everything stripped of structure, stripped of identity. All that's left is the raw, charged feedstock of matter, utterly dominated by the magnetic environment. This thought experiment shows the absolute, unforgiving physics of the place. The surface of a magnetar isn't just an extreme version of a planet or a star. It's an environment where the very concept of solid matter becomes meaningless. The forces there rewrite the rules of atomic cohesion. No known material could maintain its integrity. No conceivable material. It might be the most definitively hostile surface in the entire cosmos, a realm where reality's architecture is drawn not by chemistry or gravity alone, but by magnetic force. A force of almost divine potency, and that leaves a haunting question: if matter cannot survive there, what signatures of that power could we even detect? From the safety of our own solar system, the universe keeps its secrets in different ways. Some of them shout, some of them are quiet. For a long time, astronomers were finding these objects that didn't do either. They were called anomalous X-ray pulsars, and the fact that they were silent, that was the clue. They weren't like regular pulsars. They didn't send out those steady radio signals. And they weren't like the soft gamma repeaters either. Those things have these huge, violent outbursts. These objects didn't do that. They were just there. Just glowing, a constant, steady shine in X-ray light. They did pulse, but only in that high-energy band. Every few seconds, they were complete anomalies. Their energy was a mystery, because if it was just a neutron star slowing down like a normal pulsar, that couldn't explain it. The glow was too bright, too powerful. There had to be another engine, and the answer, it turned out, was magnetism again, the most extreme kind. These were magnetars, just in a different stage. You can think of a soft gamma repeater as a magnetar when it's young and stormy. Its crust is cracking. It has these starquakes, these flares. An anomalous X-ray pulsar is that same object, but older. More settled. The magnetic fury hasn't gone away. It's just found a different way out. Here, the power comes from the magnetic field itself decaying. Slowly, it's a process called magnetic breaking. The field lines are wound unbelievably tight, under incredible tension, and they slowly twist, they writhe, trying to find a lower energy state. And as they move, as they subtly snap and reconnect in the star's atmosphere, they release energy, not in one big explosion, but in a constant, powerful simmer. That constant magnetic activity heats the surface of the neutron star to millions of degrees, and that's what makes it shine in X-rays. It's like a perpetual, luminous sigh. A sigh of magnetic stress. Realizing these were magnetars, that was a revelation. It completed the picture. It showed these objects aren't just about the big explosions. The magnetic dominance is constant. It's a lifelong condition. For tens of thousands of years, the internal dynamo fuels this quiet, radiant output. It gives us a stable window. Like a laboratory light left on. So we can study these fields. We don't have to wait for a starquake. The whisper from the AXP is always there, telling us about the slow, relentless dissipation of the strongest force there is. It shows the magnetic fury isn't an event. It's the state of being. The deepest thing about a magnetar is that it can make something from nothing. It builds matter out of the dark. That's not magic. It's quantum mechanics taken to an absolute extreme. It's a process called pair production. It starts with the fact that the vacuum of space isn't really empty. At the quantum level, it's a seething, bubbling sea of potential. Pairs of particles and their antiparticles, like an electron and a positron, they constantly wink into existence for just an instant. Then they annihilate each other and vanish. In our part of the universe, this is ghostly, invisible. But near a magnetar, the magnetic field is so strong it seizes these ghost particles. It provides the huge amount of energy needed to rip them from the quantum foam and make them real, permanent. The field acts like a cosmic loan shark. It offers the energy to materialize the pair. And in return, the newborn particles are instantly enslaved by the force that created them. They are caught, whipped into motion along the impossibly curved magnetic field lines, accelerated to nearly the speed of light in a fraction of a second. And when charged particles are forced to race along curved paths that fast, they have to pay an energy toll. They shed their excess energy as light, but not just any light. They emit torrents of high-energy X-rays and gamma rays. That's synchrotron radiation, a brilliant, lethal glow born from magnetic imprisonment, so you get a self-sustaining furnace. The magnetic field creates particles. Those particles, racing along the field, emit radiation that can help create more particles. This builds up a churning, dense atmosphere of magnetized plasma around the star. Astronomers call it a magnetosphere. It's a hellish aurora, powered not by solar wind, but by the raw conversion of magnetic energy into matter and light. So the magnetar doesn't just distort the universe it's in. It actively populates a new one. From the apparent void, it summons a storm of existence, a perpetual, luminous testament. Under conditions of ultimate force, the line between empty space and tangible stuff isn't a wall. It's a curtain waiting to be pulled aside. That magnetic furnace doesn't only make light. It starts to shape the stage itself. Space-time, in Einstein's view, gravity isn't just a force from mass. It's the curve in space-time from energy. And the energy in a magnetar's magnetic field is a colossal store. The density is so huge it actually bends the fabric of the universe around the star. So the gravity you'd feel near a magnetar, that's not just from its mass. A big part of that pull is from the raw energy of its trapped magnetic field, which means something. The bending of light, gravitational lensing, would be stronger than you'd think from mass alone. A light ray grazing the star wouldn't just be deflected by gravity. It'd get an extra pull from the warp caused by the magnetic energy itself. Lensing, but powered by magnetism. Then there's spin. Magnetars rotate so fast some turn in seconds. A massive object spinning that fast doesn't just sit there. It drags the fabric of the universe around with it, like a spoon in thick honey. That's frame dragging. Near something city-sized with a star's mass spinning that fast, the effect is huge. Space and time aren't just curved. They're twisted into a spiral around the star. So you put these together. The deep gravity well from the mass, the extra curve from the magnetic energy, and the spiraling whirlpool from the frantic spin. What you get is a space-time geometry of incredible complexity. A knot of warped dimensions where here and now get tangled. Modeling this pushes supercomputers to their limit. It's a puzzle where magnetism and gravity aren't separate anymore. They're partners, reshaping reality into forms we can hardly calculate. Which means to really understand a magnetar, you can't just study its gravity or its magnetism alone. You have to see it as one engine, a unified engine of space-time distortion. Its deepest mark on the cosmos might not be the light it gives off. It might be the silent twisting of the universe's fabric around it. A permanent scar in geometry written in magnetic fire. The most dramatic thing a magnetar does is produce a giant flare. It's a cosmic explosion so powerful it can briefly outshine entire galaxies. These events are incredibly rare, maybe once every few decades in our own Milky Way. But when they happen, they change what we think is possible. In just a tenth of a second, a giant flare can release more energy than our sun will put out over 100,000 years. And all that energy is focused into a narrow beam of gamma rays, the most energetic form of light. On December 27, 2004, our planet was in the path of one of these beams. It came from a magnetar called SGR 1806-20, about 50,000 light-years away on the far side of our galaxy. For a fraction of a second, this wave of gamma rays, traveling for millennia, washed over our solar system. Satellites meant to study the sun were blinded. The radiation was so intense it ionized the upper layers of Earth's atmosphere. It disturbed long-range radio communications. We felt the breath of a starquake from halfway across the galaxy. But the story gets bigger. These flares are so bright we can see them from outside our own galaxy. In April 2020, an observatory saw another immense flash. Its origin wasn't in the Milky Way. It came from a magnetar in a galaxy called NGC 253. Over 11 million light-years away. That was a monumental confirmation. The physics behind these eruptions is so universal, so reliably extreme, that it creates a recognizable signal across intergalactic space. That turns a giant flare into something useful, a standard candle. In astronomy, a standard candle is an object with a known intrinsic brightness. You measure how dim it looks from Earth, and you can calculate its distance. It's like knowing the true wattage of a light bulb. Seeing how faint it looks tells you how far away it is. Magnetar giant flares, with their staggering and predictable peak brightness, are becoming the ultimate cosmic light bulbs. They let us measure distances to far-off galaxies with new precision, helping to map the expanding universe itself. But the light from these flares does more than mark a location. On its multi-million-year journey to us, that beam of gamma rays and X-rays travels through the vast, mostly empty spaces between galaxies. It interacts with the sparse atoms and particles floating there. The intergalactic medium, by analyzing how the flare's light has been filtered and altered after that epic voyage, astronomers can probe this mysterious cosmic web. They can sense its density, its composition, the magnetic fields threading through the void. So each giant flare is two gifts in one: a brilliant beacon that pinpoints a galaxy on the cosmic map, and a powerful searchlight, illuminating the invisible structure of everything between us and it. In their brief, violent lives, these magnetic monsters illuminate the darkness in ways we are only starting to understand. This crust is a landscape of absolute extremes. A shell may be a kilometer thick, and inside that thin skin, the pressure is so high that a sugar cube of that material would weigh more than Mount Everest. It's not rock. It's a quantum crystal, a perfect, rigid lattice of iron nuclei squeezed by gravity until they're almost touching. The electrons that should orbit those nuclei, they are not bound to atoms anymore. They've been crushed into a degenerate sea, a frictionless quantum fluid that flows right through the nuclear lattice. It's a metal, but not like any metal we know. 1 billion times stronger than steel. The entire crust of a city-sized star with the mass of a sun is held up by this bizarre, crystalline skin. And through this skin, the magnetic field threads. Like iron rods frozen into ice, those field lines are anchored deep below, in the star's superfluid, superconducting core. That core is a chaotic dynamo, always churning, always evolving. And as it twists, it drags the roots of these magnetic cables with it. But up here, at the surface, the cables are frozen into the rigid crust. So when the core moves, it applies an unimaginable torque. The crust is locked in a tug-of-war, twisted from below by the fluid core, while its own incredible strength resists. The stress builds. For years, decades, centuries. Until it can't. The crust doesn't bend, it breaks. A fracture races across the star's surface, probably spanning the whole circumference. That's the Starquake. In that single, catastrophic slip, the crust settles, maybe a centimeter, but that tiny movement under these conditions releases more energy than our sun emits in 100,000 years. All of it floods out as a flash of X-rays and gamma rays, the giant flare we detect from across the galaxy. For scientists, that flash is just the start. The quake sets the whole star ringing, like a bell. The vibrations, called asteroseismic modes, travel through the crust and into the core. By studying the flickering X-ray afterglow of a flare, astrophysicists can detect these subtle tones. Like a geologist learning about Earth's interior from seismic waves, these cosmic vibrations reveal secrets. The frequency of the ringing tells us about the crust's elasticity, how stiff this quantum crystal really is. The way the vibrations dampen tells us about the boundary between the solid crust and the liquid core beneath. And that core is the final mystery. Beneath the crust, density increases to a point where our physics blurs. Nuclei might dissolve into a soup of free neutrons and protons, possibly even stranger things. Some theories suggest the neutrons themselves might break down into their constituent parts, a sea of free quarks. The vibrations from a starquake are our only probe into that alien realm. They carry whispers about the state of matter at densities so high they approach the fundamental limits of existence. Each starquake is a hammer tap on the universe's most exotic bell, and the tone it rings out is a direct message about the fabric of reality under conditions we can never recreate. That magnetic fury has a clock running. Even the strongest force there is can't last forever. A magnetar's field, that quadrillion Gauss strength, it's a huge store of energy. But it's not permanent. It's a temporary state, a brilliant one, but temporary. The engine is winding down, and what drains it is something called ambipolar diffusion. It's as exotic as the star itself. Picture the interior below the crust. It's a superfluid, a superconducting soup of neutrons with some protons and electrons in there. The magnetic field is frozen into that quantum fluid. But the pieces don't all move together. The charged particles, the protons and electrons, they're locked to the magnetic field lines. The neutrons aren't. So the field, under all that tension, wants to relax, to rearrange, and as it tries, it tugs on those charged particles. They begin to drift. A very slow drift through the sea of neutral neutrons. That drift is ambipolar diffusion. It's incredibly slow, but the consequences are immense, because that slow motion of charged particles is an electric current. And any current moving through a medium creates friction. Even in a superfluid, it makes heat. In a magnetar, that internal magnetic friction heats the core to an incredible degree. That thermal energy works its way out to the surface, and it radiates away as X-rays, that steady glow we see from anomalous X-ray pulsars. So every one of those X-ray photons is a direct withdrawal from the magnetic field's energy account. The star is shining by spending its magnetic fortune. The timescale for this decay is brief, cosmologically. In about 10,000 years, the field weakens significantly. 10,000 years is a long time for us, but for a stellar corpse that could live for billions of years, it's a blink. This decay sets the magnetar's whole active life. As the field weakens, the stresses on the crust lessen. The starquakes get less violent, less frequent. The giant flares stop. The steady X-ray glow from the decay fades, from a shout to a whisper, then to silence. What's left is still a neutron star, that city-sized sphere of impossible density. But its defining personality, that monstrous magnetic rage, has faded. It might become a more ordinary pulsar, beaming radio waves powered by its spin slowing down. Not by magnetic fury, or it might just go quiet. A dark cinder, drifting through the galactic void. Its era of violence a distant memory. That life cycle frames the magnetar not as a permanent monster, but as a phase. A brilliant, furious, fleeting adolescence in the billion-year life of a neutron star. It's a transient window, a brief period where conditions are just right for the universe to twist matter and energy into their most extreme forms. We're lucky to live when we can see this phase in some of these stellar corpses. Their intense activity makes them visible across the galaxy. It lets us study physics at the absolute limit, but their impermanence adds something, a layer of meaning. Every detection, every starquake we record, it's a snapshot of a cosmic event that's over on the grand scale. Almost as soon as it starts, we're catching the universe in a moment. A moment of spectacular, magnetic rage. We've only confirmed about 30 of these things in the whole galaxy. Something that rare, that violent. It takes a different kind of astronomy to find it. A detective hunt across every wavelength. You don't start with visible light. You start with the high-energy signs of magnetic fury. Satellites like Swift and Fermi, they're always scanning. Their instruments are tuned for that sudden flash of gamma rays. A starquake happening right now, a giant flare. When they catch one, they send an alert. And the hunt begins. Other satellites like Chandra and XMM-Newton, they specialize in X-rays. They look for the steady, hot glow from a magnetar's magnetic field. Or they catch the precise, clockwork pulsations, a rapid ticking in X-ray light, coming from a point where no star should be. Those high-energy observations give you the first clues. A position, a spin period, an energy profile, but to really understand the beast, you need to see it in every kind of light. So then you turn to radio telescopes. Sometimes, not always, a magnetar will also emit pulsed radio waves. Detecting that confirms it's a neutron star. It gives you an even more precise measure of its spin, and how that spin is slowing down. Then the search moves to optical and infrared. Can you see a faint, visible star at that exact spot? Usually, no. The magnetar itself is too dim in ordinary light. But sometimes those observations show you something just as important. The ghostly, expanding shell of a supernova remnant. The glowing wreckage from the star's explosive birth, still lingering around it like cosmic smoke. Finding that remnant is like finding a crime scene. It confirms the violent origin. It helps pin down the object's age. This whole painstaking, collaborative process, that's how a candidate becomes a confirmed magnetar. It's a triumph of modern, global astronomy. But the hunt is full of frustration because these objects are masters of disguise. They can be transient. A magnetar might scream with a giant flare, announce itself with galactic fanfare, and then fade back into a quiet, X-ray glow for decades. Or it might go quiet for a long time, becoming invisible to all but the most sensitive X-ray eyes. Every new discovery, every hard-won confirmation, is a treasure. It expands our tiny sample of these natural laboratories. It gives theorists new data. Data to test their models of nuclear matter, magnetic field decay, Starquake physics. Every point of light added to the map of known magnetars is a new extreme data point. Another mark on the graph of what's possible in our universe. The search for magnetars keeps running into other mysteries, like fast radio bursts. For years, astronomers have been detecting these signals. They're bursts of radio waves incredibly bright, but they only last milliseconds. They come from far outside our galaxy, sometimes billions of light years away. Their origin was a huge puzzle. Theories included merging black holes, even alien transmitters. Then in April 2020, something happened. A known magnetar in our own galaxy, SGR 1935 plus 2154, had an outburst. It produced a starquake, a burst of X-rays, but telescopes caught something else too. A millisecond blast of radio waves. It wasn't as powerful as the distant fast radio bursts, but its signature was the same. The intensity, the duration, the signal structure. A perfect match, just closer and quieter. That was the smoking gun. For the first time, a known object, a magnetar, had produced a fast radio burst. It meant that at least some of those distant flashes could be magnetars in other galaxies. The mechanism is probably tied to the same violent processes we see. A catastrophic starquake, or a sudden reconnection of magnetic field lines. An event that shakes the star and its plasma so violently it sends out a lighthouse-like beam of coherent radio waves. If a magnetar here can do it, then a younger, more violent one in a distant galaxy could certainly produce the far more energetic signals we see. This connection is deep. It puts magnetars at the center of two big puzzles: their own extreme nature and the origin of fast radio bursts. It changes them from exotic curiosities into potential universal engines. Their physics, tested nearby, might explain some of the most energetic transient signals we see from the farthest reaches of space. They become a key. A key that could unlock not just the nature of matter under extreme pressure, but the meaning of mysterious flashes that have traveled across voids for billions of years. The purpose of a lab is to go into the unknown, and that's what a magnetar is. It's a physics experiment, but on a cosmic scale. The conditions are so extreme, the temperature, the density, the magnetic force, that we can't match them. Not even with something like the Large Hadron Collider. We can't bring a magnetar into a lab, so we use the universe instead. We watch its output as data. From a natural experiment, Take the quantum vacuum. Here, it's an abstract idea. A seething foam of virtual particles you can't see. But near a magnetar, the field is so strong it polarizes that nothingness. It forces the vacuum to behave in ways we can measure. It bends light, it splits light, and that lets astrophysicists test quantum electrodynamics, our theory of how light and matter interact. They test it under the most severe stress possible. Any tiny deviation between what we see and what the theory says, that could be a monumental clue, a whisper of new physics. A crack in our understanding, and it's only visible because a magnetar twisted the void to its breaking point. Then there's the core. Beneath that iron crust at supranuclear densities, matter is compressed. Our standard model begins to strain. Protons and neutrons, the familiar building blocks, they might not survive. They might dissolve into their constituent quarks and gluons. A soup of free quarks. Or under that pressure at those low temperatures, that quark soup might organize into something even stranger, a color superconductor, where particles flow with zero resistance. Other theories suggest exotic particles, like pions, condensing into a giant, star-sized Bose-Einstein condensate. These aren't just imaginative ideas, they're serious predictions for matter under ultimate compression. And a magnetar's vibrations, the asteroseismic tones after a starquake. That's our only probe. The way the star oscillates and settles tells us about the stiffness inside. It gives us indirect evidence for what phase the matter is in. So every flicker of X-ray light, every precise pulse, every afterglow from a giant flare, it's more than a cosmic event. It's a data point, a point on a graph, charting the laws of nature under conditions we can never create. By collecting this data, scientists are doing remote experimental physics. They're using the magnetar's violence to ask profound questions. What is the true nature of the vacuum? What happens to matter when it's squeezed beyond atoms and nuclei? Does our map of fundamental forces hold, or does it finally show its edges? In the silent depths of space, these magnetic monsters are running the experiments for us, broadcasting the results in a language of light, and we are steadily learning to translate it. That power, the kind that reshapes atoms, it makes you think of home. Could something like that ever be a danger to us here? It's a natural question. The simple answer is that Earth is, for now, wonderfully safe. Space is mostly empty. The closest known magnetar is thousands of light years away. At that distance, even its most violent outbursts reach us only as data. Interesting data, not a destructive force. The scale of safety is measured in light years. For a giant flare to damage our biosphere directly, the star would have to be catastrophically close. Within 10 light years or so. At that range, the pulse of gamma and X-ray radiation could strip away part of the ozone layer. The consequence would be more ultraviolet radiation reaching the surface. That would have profound implications for life. In the long history of life on Earth, there have been mass extinctions. Their ultimate causes are still debated. Some scientific discussions have explored the possibility of a nearby stellar explosion. A supernova or an extreme gamma-ray burst could have been a factor in the distant past. But it's important to note, no evidence currently links any historical event specifically to a magnetar flare. The probability is vanishingly small. A magnetar would need to be born close enough, and then erupt during the brief window of human civilization. The cosmic perspective is reassuring. It lets the view shift from worry to wonder. These are universe-shaking phenomena, titanic demonstrations of physics at its most extreme. But the immense distances transform their fury into a spectacle, a brilliant, distant light show. It allows scientists to study fundamental laws under impossible conditions. We can observe their starquakes, decode their flares with a sense of awe, not fear, secure in the knowledge that the void itself is our shield. Their terrible beauty is a gift. A remote laboratory, broadcasting secrets from the edge of reality. The problem with a magnetar is we can't build one, we can't get near it. So you have this object that's mostly theory, a faint signal from far away. And the way you study it, you build one digitally, inside a supercomputer. That's where computational astrophysics is now. You take the equations of reality and turn them into code. You simulate the universe, one calculation at a time. You start with the fundamental laws, the equations for magnetohydrodynamics, how magnetic fields interact with a conducting fluid. Then you add Einstein's equations for general relativity because space-time is curved. And you bring in quantum mechanics for matter at nuclear density. Putting all that into one coherent model, that's a huge task. It's like writing a recipe that accounts for the flow of honey, the strength of steel, and the rules of a ghostly particle zoo. All while the pot itself is twisting. Running that model, even for a simulated second of a magnetar's life, can take millions of CPU hours on the most powerful supercomputers. The goal is to visualize what's invisible, to watch the magnetic field frozen into the star's superfluid core as it slowly writhes and twists, to see stress build in the rigid iron crust above it. And then to see the moment that crust fractures, triggering a digital starquake, a simulated flare of radiation. What comes out isn't just an animation. It's a detailed prediction. It tells theorists what kind of X-ray flicker to expect after a quake. It predicts how the star's spin should change after a major flare. It even suggests what kind of ripples in space-time gravitational waves that kind of cataclysmic rearrangement might produce. Then you compare those predictions, point by point, with actual data from telescopes. When the simulation matches the observation, that's a triumph. It means our understanding of the physics, coded in those millions of lines, is probably correct. When it doesn't match, that's even more exciting. It means the simulation has shown a gap in our knowledge. Maybe the crust is stranger, or the core more exotic than we assumed. Each mismatch is a guidepost, pointing toward new physics. So these supercomputer simulations act as a digital telescope. They peer into places no instrument can go. They let us run experiments on a star we can never touch, test theories we can never prove in an Earth lab. They turn the magnetar from a distant mystery into an interactive model. A cosmic puzzle you can take apart and put back together, over and over, until its secrets finally come into view. The ripples from a starquake move through the star, and then they move out. They travel through the universe, through spacetime itself. That's the next clue, gravitational waves. When a magnetar's crust fractures, when its magnetic field snaps and reconnects, the whole star jolts. It rings, and that ringing distorts the space around it, sending out these faint ripples at light speed. We've built ears to listen. LIGO and Virgo, these observatories on Earth, they can sense distortions smaller than an atom. They've heard black holes colliding, neutron stars merging, and they're listening for the chirp, the burst that might come from a magnetar quake. Then there's LISA, the future observatory in space. It'll be quieter there, tuned to different vibrations. Detecting those waves from a magnetar would change everything. It'd be like going from a photograph to an ultrasound. Light shows you the surface, the aftermath. But gravitational waves let you hear the interior event as it happens. The signal's frequency, how it decays, it carries direct information. About the crust's rigidity, the core's density, the exotic matter inside, that's multi-messenger astronomy. You wouldn't rely on one distorted message. You'd combine the gravitational wave sound with the X-ray light, the gamma-ray light from the same event. Like watching a silent film of an explosion while hearing the detailed sound of the blast. Each sense informs the other. You build a complete picture. A picture of a magnetar in crisis, from its tortured interior to its radiant magnetosphere. That combined data would test our models. Models of nuclear physics under ultimate density under that magnetic stress. It could confirm what we think. Or it could rewrite it. Rewrite our understanding of matter pushed beyond every known limit. The future isn't just about seeing deeper, it's about learning to listen. To hear the universe's most powerful magnets ring. The idea of a magnetar, its destructive power, that's something that moves from science into the stories we tell. A star whose presence alone could wipe out a world's technology. Or you could take that magnetic fury and turn it into a weapon, the ultimate cosmic weapon. Creators can't resist it. In science fiction, they've become the new black hole, a shorthand for something terrifying and exotic and powerful. In novels, they're a navigation hazard. They can shred a starship down to its atoms. In video games, they're a mysterious power source for some ancient civilization that spanned a galaxy. On television, they're a cosmic time bomb. Their Starquakes threaten entire sectors of space. This cultural footprint, it's more than entertainment. It's a translation layer. The actual astrophysics, magnetic field decay, quantum vacuum polarization, it's dense. It's abstract. But a story about a starship crew navigating desperately around a magnetar's lethal magnetosphere. That translates the science, it turns it into stakes. You can feel it. It turns data points into drama, and that sparks a curiosity. A public curiosity that pure equations often can't reach. Someone encounters a magnetar in a game or a book, and they might look it up. They learn this fantastical object is real. That bridge from fiction to fact, that's where inspiration lives. It reflects a timeless fascination. We're drawn to the edges of the known. To where the universe shows its absolute power. Magnetars in both science and story, they sit right on that frontier. A natural force so supreme it bends the rules of reality. By weaving them into narratives, storytellers tap into that primal awe. They give it a name, a face, or a terrifying, luminous character for the cosmic unknown. And this exchange, it flows both ways. Scientific discoveries provide the raw material, thrilling material for new myths and adventures. And in return, those stories make the cosmos feel less like a distant catalog of data. More like a grand, epic landscape, something waiting to be explored. They remind us the universe isn't just a place of cold equations. It's a source of endless wonder, capable of igniting our imagination as powerfully as it forges stars. The greatest laboratories are the ones that keep asking questions we can't fully answer. And for all we've learned about magnetars, they're still cosmic enigmas. Their deepest secrets are locked behind walls of unimaginable density and force. The very beginning is still a puzzle. We understand the broad strokes of their birth. The rapid collapse, the spinning dynamo, but the precise recipe that amplifies a field to a quadrillion Gauss, that's still elusive. What exact combination of spin and temperature and fluid motion, in those first chaotic seconds, tips a normal neutron star into a magnetic monster? Computer models get us close. But the true mechanism is a detail hidden in the fire of a supernova. A detail we can only infer from the powerful adult it creates. Then there's the core. Our maps of matter end at its edge. We know gravity crushes the interior to densities where atomic nuclei dissolve. But into what? A superfluid sea of neutrons. Or does the pressure break those neutrons apart into a soup of free quarks? A state of matter theorized but never confirmed. Some models suggest even stranger possibilities. Bose-Einstein condensates on a stellar scale. The vibrations from Starquakes are our only sonar into this abyss, and their tones are subtle, open to interpretation. The true state of matter at the heart of a magnetar is perhaps the ultimate question in high-density physics. Their entire life cycle is a timeline of decay we are still charting. We see the youthful fury of the soft gamma repeater, and the settled glow of the anomalous X-ray pulsar. But the transitions between these stages, the precise rate at which that awesome magnetic fortune is spent, that's a slow-motion process we've only observed in fragments. This decay links to a bigger family mystery. Are magnetars a distinct class of object, or are they simply one extreme phase in the life of many neutron stars? Could a pulsar, under the right conditions, become magnetically active again? The boundaries between these stellar corpse varieties are blurrier than we once thought. Even their most dramatic cosmic signatures come with asterisks. The connection to fast radio bursts is a monumental clue. But is it the whole story? Could magnetars produce all of these mysterious millisecond flashes? Or are they just one type of engine in a universe full of capable catastrophes? Every new detection sharpens the question, and so each observation, each flicker of X-ray light from across the galaxy, is a piece of a puzzle we are still assembling. These unanswered questions aren't a failure of science. They are its engine. They drive more sensitive telescopes, more powerful supercomputer simulations, more elegant theories. Magnetars force us to confront the limits of our knowledge, to stretch our understanding of physics until it strains at the seams. They ensure that for decades to come, these magnetic giants will remain at the frontier, not as solved problems, but as brilliant, demanding teachers in the dark classroom of deep space. Data comes from deep space as whispers of light. To hear them, we built ears of metal and glass, orbiting above the atmosphere. Our map of magnetars is drawn by a fleet of observatories, each tuned to a different part of their violent song. The steady, hot glow from their surfaces, that's the domain of X-ray telescopes. On the space station, there's an instrument called NICER, the Neutron Star Interior Composition Explorer. It performs a kind of cosmic cardiology. It doesn't just capture X-rays, it times them with extreme precision down to nanoseconds. By tracking the subtle changes in the X-ray pulses as the star spins, NICER can map the hotspots on a magnetar's surface. Regions heated by magnetic footpoints. It can probe the star's size and density, placing limits on the nature of ultra-dense matter. It's like using the flicker of a candle to measure the shape of the room it's in. For a wider view, we use the Chandra X-ray Observatory. Chandra acts as a sharp-eyed cosmic historian. It looks at the magnetar itself and at the space around it. Often, it captures the faint, expanding shell of the supernova remnant that gave the magnetar birth. These high-resolution images tell us the object's age, the energy of its explosive origin. They show how the magnetar's powerful wind of particles interacts with, and sometimes reshapes, the ancient debris of its parent star. Chandra provides the context, the crime scene photo that places the suspect in a timeline. But magnetars are defined by their outbursts. For those, we need instruments that catch the highest energy screams. Satellites like Integral and the Fermi Gamma Ray Space Telescope are on constant patrol. Their detectors are built for sudden, catastrophic brilliance. When a magnetar's crust snaps anywhere in our galaxy, these observatories see the flash. They measure the energy spectrum of the giant flare in gamma rays, the precise shape of its rise and fall. This data is the raw seismograph of the Starquake. It tells theorists exactly how much energy was released and in what form. These are the sentinels, waiting years for a single, milliseconds-long event that rewrites a chapter of astrophysics. The story doesn't end in space. On the ground, a new generation of radio telescopes listens for the echoes of that violence. Facilities like CHIME, the Canadian Hydrogen Intensity Mapping Experiment, scan the entire northern sky every night. They are designed to catch fleeting, millisecond bursts of radio waves, the kind linked to magnetar activity. And on the horizon is the Square Kilometre Array, the SKA. When completed, it will be the most sensitive radio ear ever built, capable of detecting the faintest pulses from magnetars across the galaxy, potentially pinpointing the radio whispers from distant fast radio bursts with new clarity. This is the synergy of modern astronomy. We are no longer looking through a single keyhole. We have built a whole wall of windows, each with a different filter. The X-ray view gives us the star's heartbeat and temperature. The gamma-ray view captures its tantrums. The radio view catches its coherent whispers. And soon, gravitational wave observatories will let us feel its interior tremors. Each dataset is a fragment of the truth. Alone, they are intriguing. Combined, they form a portrait of a magnetic monster, pieced together photon by instruments that are, in the end, the sharpened tools of human wonder. Our understanding of matter is local. It's a set of rules written for a quiet corner of a galaxy, under a gentle sun. But magnetars tear that rulebook apart. They show that the solidity of a table, the stability of an atom, the nature of light itself. These aren't universal constants. They're peaceful exceptions. Temporary agreements in a cosmos that can make far more violent contracts. In the grip of a magnetar's field, the atom is redesigned. Chemistry, the dance of bonding that builds our world, becomes impossible. What we call reality is just one possible configuration. One setting on a dial of cosmic forces, and that dial can be turned to settings of unimaginable extremity. That's a philosophical shift. It moves the discussion from astrophysics to ontology, from what is to what can be. We're not just studying a star, we're studying the outer boundaries of existence. The universe isn't just larger than we suppose, it's more fundamentally varied. The matter we're made of isn't the default state of the cosmos, it's a special, fragile case. A delicate arrangement that only persists in environments of profound calm. And thinking about that does two things. First, it brings a profound humility. Our entire physical experience, our bodies, our technology, our world, are built from principles that are utterly provincial. They don't govern the heart of a magnetar. They don't govern the core of a neutron star. In the grand arena of the universe, our normal is a niche, a quiet backwater where forces are balanced just right for something like us to emerge. That perspective shrinks our ego, but it doesn't diminish our significance. It leads to the second feeling, a staggering sense of wonder. The fact that we can perceive this, that we can build instruments to detect these realms we can never visit, that we can use mathematics to comprehend forces that would annihilate us, that's extraordinary. Our quest to understand the magnetar isn't a dry academic exercise. It's an act of cosmic reach. It's the mind, born in that quiet backwater, striving to map the furious storms at the edge of all possibility. In that endeavor, magnetars become more than objects. They become teachers. They show that the universe isn't just a collection of things, but a spectrum of states. A continuum of realities, most of which are forever closed to us, and yet we can learn to read their signatures. They affirm that the human drive to explore, to decode, to understand the most violent and alien phenomena, that's not a distraction. It's a central part of our story. By looking out at these magnetic monsters, we are, in a real sense, looking into a mirror. But it doesn't show our faces. It shows the limitless capacity of our curiosity. We're defining our place not by our physical location, but by the expanding horizon of our comprehension. The magnetar, in its terrible, beautiful isolation, whispers a reminder across the light years. The cosmos is built from wonders we have only begun to name. We don't end with an answer, we end with a different question. The magnetar story, it starts with a giant star collapsing, then it goes to space itself bending. These aren't just points of light. They're like experiments, violent ones, testing how quantum mechanics and gravity meet, under pressure that breaks what matter even means. They're natural labs, showing things no machine on Earth could show, and that's the point. Magnetars are essential, they are probes, sentinels right at the edge of physics. They tie together how stars live and die, matter at nuclear density, the forces that shape everything. They show our understanding is always provisional. Always waiting for the next observation from deep space. Neil deGrasse Tyson said it once, the universe isn't obliged to make sense to you. Magnetars are that. Glorious, confounding, necessary for the map. So let this be a start, a spark. The universe is full of extremes like this, just past our sun's light. If this dive into magnetic monsters held you, there are more mysteries. Consider subscribing for more journeys like this, and we'd like to hear from you. What about these magnetic giants gets you? What mystifies you most? Share that in the comments.